probability, and probability distributions. The topic of biostatistics and research methodology, applied mathematics, biostatistics, and statistics. Content of this topic includes probability, basic terminology in probability, classical probability equation, probability distribution, binomial distribution, normal distribution, standard normal distribution, Poisson's distribution, and comparison of types of distribution. Definition of probability. Probability is the likelihood of an occurrence, expressed by the ratio of the actual occurrences to that of all possible occurrences. Probability is a measure of uncertainty. Probability is the science of how likely events are to happen. Probability is a numerical measure of the likelihood that an event will occur. For example, coin toss, the game of heads and tails. One could reasonably guess that the probability of a head or tail is 1/2 or 50%. 1/2 of the outcomes will be head, and 1/2 will be tail. Probability of tablet formulation, defective, or acceptable, means not defective. Basic terminology, improbability. Trial and events. Performing a random experiment is called a trial. An outcome, or a combination of outcomes, is called as event. Events are also termed as cases. Exhaustive events. The total number of possible outcomes of a random experiment is called as exhaustive events. Mutually exclusive events. Two or more events are said to be mutually exclusive if the happening of any one event excludes the happening of all others in the same experiment. Mutually exclusive events cannot occur simultaneously. If one event is observed, the other events cannot occur. Independent events. Events are said to be independent of each other if happening of any one of them is not affected by, and does not affect, the happening of any one of others. Classical probability equation. For any random experiment, probability of an event A denoted by P in bracket A. Equation is favorable number of cases to A divided by exhaustive number of cases, symbolically M divided by N. Simple form of probability equation is number of favorable outcomes divided by total number of possible outcomes. P is the probability of the event happening, and Q is the probability of its not happening. P plus Q is equal to 1. The value of probability is always between 0 to 1. Probability of A is equal to 0. Then event A, called as an impossible or null event. Probability of A is equal to 1. Then event A, called as certain event. Exercise. Explain probability with example of tossing 3 coins and probability of all possible occurrences. Outcomes of tossing a coin are head or tail. When 3 coins are tossed, The possible outcomes are 8. All possible outcomes of 3 coins tossed together is as shown here. First, calculate probability for chance of getting only heads. Probability of all 3 heads is number of outcomes of all 3 heads divided by number of all possible outcomes. Number of outcomes of all 3 heads is only 1, and number of all possible outcomes is 8. So, probability of all 3 heads is 0.125. Now, calculate probability for chance of getting 2 heads. Probability of 2 heads is number of outcomes of 2 heads divided by number of all possible outcomes. So, probability of 2 heads is 0.375. Calculate probability for chance of getting at least 1 head. Probability of getting at least 1 head is number of outcomes of getting least 1 head divided by number of all possible outcomes. Probability of getting at least 1 head is 0.875. Calculate probability for chance of getting only 1 head. Probability of getting only 1 head is number of outcomes of only 1 head divided by number of all possible outcomes. Probability of getting only 1 head is 0.375. Probability distribution. Definition is: probability distribution is a function that gives the probabilities of occurrence of possible events for an experiment. The description of probability by a formula, a graph, in which each event is linked to its probability, is called probability distribution. Probability distributions are a common way to describe, and possibly predict, the probability of an event. A probability distribution graph visualizes the likelihood of various outcomes for a random variable, where x-axis lists the potential outcomes, or values of the random variable, and y-axis represents the probability density, or the probability of a discrete outcome. So, based on types of the random variable, probability distribution is broadly categorized into discrete probability distribution with countable and distinct outcomes, while second category is continuous probability distribution with measurable ranges, means infinite outcomes. Discrete probability distribution assigns probabilities to specific, individual outcomes. Most common types are binomial distribution and Poisson distribution. Continuous probability distributions define probabilities over a continuous range of values. It forms smooth curve plot. Most common type is normal distribution. Binomial distribution. Synonym is Bernoulli distribution. Conditions. In binomial distribution, random experiment is performed repeatedly, a finite and fixed number of times, in trials. the random experiment results in two mutually exclusive and exhaustive outcomes, that is, success and failure. All the trials are independent, means the result of any trial is not affected to the result of other trial. The probability of success in any trial is P and is constant, that is, value of 0.5. For each trial, P is equal to 1 minus Q, and so Q is equal to 1 minus P. Example: the result of treatment with an antibiotic is that an infection is either cured or not cured within 5 days. The outcome of a patient following treatment can take on one of two possibilities: a cure or a not cure, that is failure. After performing in trials, it is found that outcome probability of cure is 0.75. So, probability of cure is P is equal to 0.75, and probability of not cure is Q is equal to 0.25. Assigning the value 1 for a cure and 0 for a failure, the probability distribution is simply F1 is equal to 0.75 and F0 is equal to 0.25. Probability distribution of a binomial outcome plot is shown here. Examples of binomial data in pharmaceutical research. LD50 determination. Animals live or die after dosing. Determine dose that kills 50% of animals. ED50 determination. Drug is effective or not effective. It determined dose that is effective in 50% of animals. Sampling for defects. In quality control, product is sampled for defects. Tablets are acceptable or unacceptable. Clinical trials. Whether treatment is successful or not successful. Formulation modification. Palatability preference of old and new formulation. New formulation is more or less available in crossover design. Expansion of the expression. The probability of the outcome of a binomial experiment consisting of n trials can be computed from the expansion of the expression. Equation is P plus Q with the power of n, where P is defined as the probability of success, Q is the probability of failure. If the number of binomial trials, n is 3, then the expansion of the expression equation is given below. Let's find out probabilities for possible outcomes for the result of treatment with an antibiotic. P is 0.75 and Q is 0.25. The equation is as here. Within this equation, P cubed is actually the probability of 3 cures. Let's put the value of P and identify probability of 3 cures. Probability of 3 cures found is 0.422. 3p squared. Q is actually the probability of 2 cures and 1 failure. Put the value of P and Q. And identify probability of 2 cures and 1 failure. Probability of 2 cures and 1 failure found is 0.422. 3p q square is actually the probability of 1 cure and 2 failures. So, identify the probability of 1 cure and 2 failures. Probability of 1 cure and 2 failures is 0.141. Q cubed is actually the probability of 3 failures, means the probability of 0 cures. Now, identify the probability of 3 failures. The probability of 3 failures is 0.016. In this example, there is only 4 possible outcomes. Let's draw a plot of probability distribution of a binomial with P is 0.75 and N is 3. For possible outcomes with probability are represented as, for bar, the particular binomial distribution shown in the figure comprises only 4 possible outcomes. Further expansion of equation. Probability function of binomial distribution is given as probability of x successes in trials is given here, where n choose x equals to n factorial divided by x factorial into n minus x factorial. N choose x is recognized as binomial coefficient. In some reference source, you may find this type of equation for probability function of binomial distribution. Exercise. Calculate the probability of 1 success in 100 trials if t is 0.01. Here is the equation of probability of x successes in n trials. Let's first find out n choose x. Put the values given for n and x. Here is the factorial calculation. To simplify factorial calculations, the core strategy is to expand the larger factorial of numerator until it matches the smaller factorial in the denominator, allowing you to cancel them out. So, n choose x obtained is 100. Now, put all values in the main equation and solve the sum. Probability of 1 success in 100 trials obtains is 0.36973. Exercise. What odds would you give of finding 2 defective tablet in a sample of size 20 if the batch of tablets has 1% defective? Here is the equation of probability of x successes in n trials. Let's first find out n choose x. Put the values given for n and x. So, 20 choose 2 obtained is 190. Now, put all values in the main equation and solve the sum. Probability of finding 2 defective tablets in 20 sample obtains is 0.0159. Next probability distribution is normal distribution. Synonym is Gaussian distribution, Gaussian law of errors. Definition is normal distribution is the frequency distribution that produces symmetrical bell-shaped curve. Properties. Normal distribution is an example of a continuous probability density function. Normal distribution is as perfectly symmetrical, bell-shaped curve. Theoretical normal distribution is a continuous probability distribution and consists of an infinite number of values, minus to plus infinite. The data points extend from positive infinity to negative infinity. Theoretically ranges minus infinite to plus infinite, but practically ranges 6 sigma, mean scatteredness of 6 standard deviation. The normal distribution is defined by its mean and its standard deviation. The standard normal curve has a mean of 0 and a standard deviation of 1. The equation for the normal distribution, that is, normal probability density function, is given below, where Px is probability function of x, sigma is population standard deviation, pi value is 3.14, e is 0.2.718, the base of natural logarithms, x is continuous random variable, mu is population mean. You may find equation of the normal distribution with different symbols, as given here, where upsilon is the ordinate of normal curve, a function of x. Let's see a typical normal curve. Top of bell is mean. The curve is symmetrical about the line. That means it is same shape on either side of the line. Mean, median, and mode are same. Central value divides whole area into 2 equal parts, with p is equal to 0.5 value. As no portion lies below x-axis, probability can never be negative. As value of x increases numerically on either side of mean, px decreases rapidly. Maximum probability occurring at x is equal to mu, that is mean value, and is given by equation px maximum. Various normal distribution plots are symmetrical and showing bell-shaped appearance. They are differentiated only by their means, a measure of location, and standard deviation, a measure of spread. The spread or shape of the normal distribution is dependent on the standard deviation. The larger standard deviation, the spread of the normal distribution is large. In real-life situations, the distribution of a finite number of values often closely approximates a normal distribution. For example, weights of tablets taken from a single batch may be approximately normally distributed. For practical purposes, any continuous distribution can be visualized as being constructed by categorizing a large amount of data in small equal length intervals and constructing a histogram. Suppose that all the tablets from a large batch are weighed and categorized in small intervals or boxes. The number of tablets in each box is counted and a histogram plotted as shown. Such a histogram can similarly be constructed for normally distributed variables. As more boxes are added and the intervals made shorter, the intervals will eventually be so small that the distinction between the bars in the histogram is lost, and a smooth curve results. Areas under the normal curve represent probabilities and are obtained by appropriate integration of equation as shown here. The total area under the curve is 100%. Phi is 1. The probability of observing a value between z1 and z2 is calculated by integrating the normal density function between z1 and z2. So, here is the plot of area under normal probability curve. The whole area under curve represents probability 1. That is, whole area is the 100% probability. The center point value is mean. The mean is the maximum probability occurring value. This mean value also divides whole area into two equal parts with probability equals 0.5. That is 50% probability at each side from the center mean value. Now, let's move from center to one standard deviation on both sides. The value of x at both ends are mu minus sigma and mu plus sigma. The area under normal probability curve between the ordinates at mu minus sigma and mu plus sigma is 0.6826. We can also say as the range mu plus or minus sigma covers 68.26% of the observations. Let's move from center to two standard deviation on both sides. The value of x at both ends are mu minus 2 sigma and mu plus 2 sigma. The area under normal probability curve between the ordinates at mu minus 2 sigma and mu plus 2 sigma is 0.9544. We can also say as the range mu plus or minus sigma covers 95.44% of the observations. Further, move from center to 3 standard deviation on both sides. The value of x at both ends are mu minus 3 sigma and mu plus 3 sigma. The area under normal probability curve between the ordinates at mu minus 2 sigma and mu plus 2 sigma is 0.9973. We can also say as the range mu plus or minus sigma covers 99.73% of the observations. Empirical rule for normally distributed data. 68% of the data fall within 1 standard deviation of the mean. 95% of the data fall within 2 standard deviation of the mean. 99.7% of the data fall within 3 standard deviation of the mean. Area under the normal probability between the ordinates or range at from x is equal to mu plus 3 sigma and x is equal to mu minus 3 sigma is 99.7%. X is equal to mu plus 2 sigma and x is equal to mu minus 2 sigma is 95%. The standard normal variate corresponding to x is z is equal to x minus mu upon standard deviation. Let's find the value of z when the x value move from center to 1 standard deviation on positive side. So put the value of x as mu plus standard deviation in the equation of z and find out z value. Z value for x as mu plus standard deviation is 1. Now, find the value of z when the x value move from center to 2 standard deviation on positive side. So put the value of x as mu plus 2 standard deviation in the equation of z and find out z value. Z value for x as mu plus 2 standard deviation is 2. Now, find the value of z when the x value move from center to 3 standard deviation on positive side. So put the value of x as mu plus 3 standard deviation in the equation of z and find out z value. Z value for x as mu plus 3 standard deviation is 3. Let's find the value of z when the x value move from center to 1 standard deviation, 2 standard deviations, and 3 standard deviation on negative side. So put the value of x in the equation of z and find out z values. Z value for x as mu minus 1 standard deviation is minus 1. Z value for x as mu minus 2 standard deviation is minus 2. Z value for x as mu minus 3 standard deviation is minus 3. Therefore, area under the standard normal probability curve between the ordinates at z is plus minus 1 is 0.6826. Between the ordinates at e is plus minus 2 is 0.9544. Between the ordinates at d is plus minus 3 is 0.9973. The standard normal probability curve has a mean of 0 and a standard deviation of 1. Now, let's put these values in the equation for the normal distribution. The equation becomes smaller, as given here. The standard normal probability curve has a mean of 0 and a standard deviation of 1. A table of cumulative areas under the standard normal curve, giving the area below z. This table is called as the z-table. Both row and column headings combination are showing the value of z, while the values present inside of the table is actually the cumulative area under curve, left size to the particular z value. Remember that this table always provides the area of the left of a given z value. Let's take an example of z value in identify area in the z-table for z is equal to 1.96. For z-value 1.96, select 1.9 and 0.06 from z-values given in the table. So, the area is 0.975. That means 97.5% of the values comprising the standard normal curve are less than 1.96. Now, identify area in the z-table for z is equal to minus 1.96. For z-value, minus 1.96, select minus 1.9 and 0.06 from z-values given in the table. So, the area is 0.025. For z is equal to 1.96, the area from table is 0.975. For z is equal to minus 1.96, the area from table is 0.025. So, the area between z equal to minus 1.96 and plus 1.96 is 0.95. The area in any interval of a normal curve of any data, with a mean and standard deviation different from 0 and 1 respectively, can be computed from the standard normal curve table by using a transformation. The transformation changes x value to z value using following equation. This equation gives the area probability between minus infinity and x. That is, the area below x corresponds to the value of the area below z from the cumulative standard normal curve table. Let's understand the use of standard normal distribution using an exercise. The U.S. Pharmacopoeia weight test for tablets. Tablets batch of a 100 milligram tablet. With N is 3 million. Mean is 101.2 milligrams. Standard deviation is 3.92 milligrams. Limits prescribed in Pharmacopoeia are not more than 2 of 20 tablets, may differ from the average weight by more than 10%. No tablet may differ from the average weight by more than 20%. We are going to test these limits for the tablet batch given in this exercise. The normal distribution is defined by its mean and its standard deviation. So if you know the same of any data set, you can directly get normal distribution plot from statistical software or from website. Let's see first limit. Not more than 2 of 20 tablets may differ from the average weight by more than 10%. Here is not more than 2 of 20. That means not more than 10 of 100. That means the limit is not more than 10%. The average weight by more than 10%. Mean given is 101.2 milligrams. Thus 10% of mean is 10.12 milligrams. Thus, limit is 101.2 plus minus 10.12 milligrams, that is 91.08 to 111.32. Now, we can quantify the limit based on this exercise. Not more than 10% tablets have less than 91.08 and more than 111.32 milligrams weight. And 90% of tablets must be in limit 91.08 to 111.32 milligrams. Now, perform the Z transformation for less than 111.32 and find the area using the Z table. X is 111.32, mu is 101.2, and standard deviation is 3.92. So, Z value obtained is 2.58. Let's check the area. Corresponds to the Z value of 2.58 in Z table. Select row of 2.5 and column of 0.08. So, answer we get is 0.995. For Z value 2.58 corresponds to an area of 0.995, that is 99.5%. Thus, probability below 111.32 milligrams is 0.995. The area below 111.32 is represented with cyan color in this plot. Now, perform the Z transformation for less than 91.08 and find area using the Z table. X is 91.08, mu is 101.2, and standard deviation is 3.92. So, Z value obtained is minus 2.58. Let's check the area. Corresponds to the Z value of minus 2.58 in Z table. Select row of minus 2.5 and column of 0.08. So, answer we get is 0.005. For Z value minus 2.58 corresponds to an area of 0.005, that is 0.5%. Thus, probability below 91.08 milligrams is 0.005. The area below 91.08 is represented with coral pink color in this plot. The Z transformation, probability below 91.08 milligrams is 0.005. Probability below 111.32 milligrams is 0.995. Thus, probability above 111.32 milligrams is 1 minus 0.995 is 0.005. Now recall to limit of pharmacopoeia. Not more than 10% tablets have less than 91.08 and more than 111.32 milligrams weight. The probability that a tablet will weight more than 111.32 milligrams or less than 91.08 milligrams is 0.005 plus 0.005 is 0.01. That is, only 1%. So only 1% of tablets have less than 91.08 and more than 111.32 milligrams weight. Conclusion: the statistician's recommendation is more than satisfied. Not more than 2 of 20 tablets may differ from the average weight by more than 10%. Let's see second limit. No tablet may differ from the average weight by more than 20%. Mean value is 101.2 milligrams. Thus, 20% of mean is 20.24 milligrams. Thus, limit is 101.2 plus minus 20.24 milligrams. That is 80.96 to 121.44. Now, we can quantify the limit based on this exercise. No tablet have less than 80.96 and more than 121.44 milligrams weight. Now, perform the Z transformation less than 80.96 and find the area using the Z table. X is 80.96, mu is 101.2, and standard deviation is 3.92. So, Z value obtained is minus 5.163. Let's check the area. Corresponds to the Z value of minus 5.163 in Z table. Select row of minus 5.1, but it is not given in the table, so we will select the lowest value of Z given here. So select row of minus 3.9 and column of 0.09. So answer we get is 0.00003. For Z value minus 5.163 corresponds to an area of less than 0.00003, equivalent to 0.00. That is 0%. Thus, probability below 80.96 milligrams is 0. Now, perform the Z transformation less than 121.44 and find the area using the Z table. X is 121.44, mu is 101.2, and standard deviation is 3.92. So, Z value obtained is 5.163. Let's check the area. Corresponds to the Z value of 5.163 in Z table. Select row of 5.1, but it is not given in the table, so we will select the lowest value of Z given here. So select row of 3.9 and column of 0.09. So answer we get is 0.99997. For Z value 5.163 corresponds to an area of greater than 0.99997, equivalent to 1, that is 100%. Thus, probability below 121.44 milligrams is 1. The Z transformation. Probability below 80.96 milligrams is 0.000. Probability below 121.44 milligrams is 1. Thus, probability above 121.44 milligrams is 1 minus 1 is 0. Now recall to limit of pharmacopoeia. No tablet has less than 80.96 and more than 121.44 milligrams weight. The probability that a tablet have less than 80.96 and more than 121.44 milligrams weight is 0 plus 0 is equal to 0, so it's a 0%. So, no tablet has less than 80.96 and more than 121.44 milligrams weight. Conclusion: the statistician's recommendation is more than satisfied. No tablet may differ from the average weight by more than 20%. The batch passes the USP test. Exercise: what is the probability that a normal patient has a cholesterol value below 170, mean is 215, and standard deviation is 35? Perform the z-transformation for less than 170 and find area using the z-table. Z-value obtained is minus 1.29. Let's check the area. Corresponds to the z-value of minus 1.29 in z-table. Select row of minus 1.2 and column of 0.09. So, answer we get is 0.09853. 4. Z-value minus 1.29 corresponds to an area of 0.09853, that is 9.85%. Thus, the probability for a normal patient has a cholesterol value below 170 is 9.85%. Poisson distribution. The Poisson distribution can be considered to be a limiting type to the binomial distribution when the sample size is large and the probability of observing a specific event is small. The Poisson distribution applied in following conditions. N. The number of trials is indefinitely large. T. The constant probability of success from each trial is indefinitely small. NP is equal to M, and it is finite. In quality control, the probability of observing a defective item is often calculated by using the Poisson distribution. In pharmacovigilance, monitoring the incidence of rare adverse drug reactions in patient populations. Dichotomous outcomes in which one of the two results has a small probability of occurrence. The binomial distribution will more than likely not produce a desired bell-shaped distribution. The Poisson process can be used to calculate probabilities associated with very large number of events, and P is relatively small. It counts the probability of number of events occurring at a fixed time. For example, number of car accident in 1 year in a city, number of mutation in particular DNA after exposure of radiation. The probability function of the Poisson distribution is given here, where lambda is NP, that is, the number of observations into probability, D is the base of natural logarithms, X is number of success. In some reference source, you may find this type of equations of Poisson distribution with different symbols of parameters, where M is NP, that is, the number of observations into probability, D is the base of natural logarithms. R is number of success. Exercise. Calculate the probability of one success in 100 trials. If probability of success is 0.01, here, the probability calculation is associated with very large number of events, and P is relatively small. Thus, the Poisson process can be used. Let first calculate lambda, that is, the number of observations into probability 100 into 0.01. So, lambda is 1. E with the power of the minus lambda is equal to 1 upon E with the power lambda is easily to calculate using calculator. Now put all values in equation and find out the probability. The answer obtained is 0.3678. The Poisson distribution is a discrete probability distribution. Since the variable x is only integer values, total probability is 1. For zero success, equation becomes probability of zero success is E with the power of minus lambda. If we know lambda, all the probability of Poisson distribution can be obtained. Thus, lambda is parameter of the Poisson distribution. In Poisson distribution, mean is equal to, variance is equal to, lambda. Comparison in binomial, normal, and Poisson probability distribution. Binomial distribution applied when random experiment is performed repeatedly, a finite and fixed number of times, and the random experiment results in two mutually exclusive and exhaustive outcomes. Normal distribution is a limiting type to the binomial distribution when the sample size is large and the probability of observing a specific event is not very small, while Poisson distribution is a limiting type to the binomial distribution when the sample size is large and the probability of observing a specific event is small. Synonym of binomial distribution is Bernoulli distribution, while normal distribution is referred as Gaussian distribution. When probability P is 0.5, binomial distribution is symmetrical shape plot. If P is less than 0.5, then it is positively skewed shape, and if P is greater than 0.5, then it is negatively skewed shape. Normal distribution is generally symmetrical, bell-shaped. A true theoretical normal distribution cannot be positively or negatively skewed. Poisson distribution is positively skewed. Binomial and Poisson distributions are types of discrete probability distribution. Normal distribution is type of continuous probability distribution. In binomial distribution, there are fixed number of trials, while in normal distribution and Poisson distributions, there are indefinitely large trials. In binomial distribution and Poisson distributions, there is only two possible outcomes, that is, success or failure. In normal distribution, there is unlimited number of possible outcomes. Binomial distribution is biparametric, featured by two parameters, n and phi. Normal distribution is also biparametric, featured by two parameters, mu and sigma. However, Poisson distribution is uniparametric, featured by only one parameter, lambda. Equations of respective distributions are given here for comparison. In binomial distribution, there is constant probability. Phi is 0.5. In normal distribution, probability is not very small. In Poisson distributions, probability of success is extremely small. Phi is nearly zero. In binomial distribution, mean is greater than variance. In normal distribution, that apply. Standard normal distribution, mean is 0, and variance is 1. In Poisson distributions, mean is equal to variance. In binomial distribution and Poisson distributions, mean is apply as NP. In binomial distribution, variance is equal to NP into 1 minus P, while in Poisson distributions, variance is equal to NP. End of the topic of probability and probability distributions. You can refer to these mentioned books for this topic. Fundamentals of Statistics by S.E. Gupta. Pharmaceutical Statistics, Practical and Clinical Applications by Sanford Bolton. Please take a note on important study questions. Thank you.